Okay, this is probably the area of chemistry where most people, most students in my experience, tend to feel very unsure of themselves. I don't know if it's because it's gone through very quickly or if the concept is a bit of an issue. So I'm gonna take a little bit of time going through these examples, specifically because it was handled in depth in the sections I did on the whole syllabus section. But here, let's just go through it. Let's just recap with this whole redox oxidation and reduction section that we're going to be talking about. First of all, what we've got here is we've got types of reactions, and remember, we've got different kinds of reactions, acids and bases. That's a proton donor kind of reaction, right? And in this situation here, we can have ion exchange. Remember those that happened? But in this type, there's a physical transfer of electrons between the one to the other. And in essence, we've got to remember the term oil rig, which is oxidation is loss, reduction is gain. Let's just make a note of that. And it's oil rig. I mean, you've all seen this, I'm sure. Oxidation is loss, and the opposite side is reduction is gain, loss and gain, right? So it's the thing that gains the electrons, okay, has undergone reduction, it's been reduced, and the one that has lost the electrons is the one that has in fact undergone oxidation, right? Now I know there's going to be terms of oxidizing agents, reducing agents, right? In essence, the way that I like to do it is we look at the oxidation and the reduction, and then I apply the opposite scenarios we've said before. Now, let's just have a look at the simple one, which is where they say they're going to give us the question where we've got a magnesium, okay? And they say magnesium and zinc chloride react to form magnesium chloride and zinc. So let's just see what we've got. We've got magnesium. So what have we done? We've actually added magnesium solid plus zinc chloride, ZnCl, are going to, and they form magnesium chloride, and they form zinc. Right? Now, let's just take a few seconds to unpack this a little quite carefully. The magnesium was a solid. Straight after this arrow over here, as I like to call it, the wall, or it's actually the activated complex situation, isn't it? We had zinc chloride there, right? Now, first of all, let's have a look. Is this balanced? Well, zinc is a +2, chlorine is a -1, Zn and MgCl2, and we've got it balanced now. So first of all, there's a few ways to look at it. We can say the magnesium solid, right? This zinc chloride is in an aqueous solution, right? So what did we do? We had zinc chloride, a salt, dissolved in water, which means we had ions floating around, didn't we? Zn +2, Cl -1. Sorry, I'm looking at the 2. -1. And we had 2 of them. So each zinc, okay, released 2 Cl minus. Right, there it is. There's 2 Cl minuses that go through there. The magnesium was a solid. Now we have to say to ourselves, well, what happened? In essence, the magnesium dissolved, didn't it? Because the magnesium now became an ion. This is an introductory way of looking at it. The magnesium became Mg +2. So, well, okay, the magnesium dissolved. It's kind of a key concept to think of, is it dissolved, okay? So the magnesium dissolved, it became an ion, and it linked up with the 2 Cl minuses, didn't it? To form the MgCl2. Remember, we had the Mg and Cl minus +2 they join together. There it is. And we had zinc solid. So the zinc actually, in essence, precipitated out, didn't it? That's what's happened here. The zinc has changed from an ion to solid. You can see it, whereas the magnesium has dissolved, right? So what happened? Well, the zinc must have got 2 electrons to do so. I know it said with oxidation numbers. We're going to get it there in a few seconds as well. We're going to look at this both ways. So the zinc has done that. Can you see the magnesium? Well, it must have given away 2 electrons, surely, to have become a +2. So therefore, we look at it and we see, first of all, are our electrons balanced? The same number of electrons, because in an oxidation and reduction environment, the electrons that are given off must be received by the opposite side. The oxidation, reduction side must balance out with each other. So what has happened over here is our oxidation and reduction has occurred. I'm going to go back. The zinc here gained electrons, didn't it? It got 2. That ion got 2 electrons and it went back to zinc, right? Remember, go right back to the, if you like, the dot diagrams, the Lewis diagrams, the electron configuration. That zinc was a +2 because it had lost the 2 electrons to the chlorine, which is the more electronegative, right? And here, it's got it back. But the magnesium has lost 2 electrons, and that's where the balance comes into it. Now we can just add them, and we can then say, therefore, Mg solid plus 2Cl minus plus Zn plus 2, there's our zinc chloride, goes to 2Cl minus plus Zn solid plus Mg plus 2, and that's our magnesium chloride, and that's our zinc chloride. And that's our balanced chemical reaction for it, right? That's the way we're going to approach these guys. Now, the other way we could have done it is we could have assigned oxidation numbers. Let's just assign the oxidation numbers with this, shall we? Let's go back to the beginning of it, because this is, as I say, a very important section, and you know what? A good understanding of this is really going to stand you in good stead. Let's go back and say magnesium solid. Magnesium solid plus ZnCl2 goes to MgCl2 plus Zn solid, like that. Now let's assign oxidation numbers, shall we? Okay, let's do it in a different color. Let's do it in green just for difference. This one is an element, so it's 0. Chlorine, the most electronegativity, the electronegative. I cannot overemphasize how important it is to do the exercises in your relevant classwork books, your textbooks, of looking at assigning the oxidation numbers to the various compounds and elements and going through those rules, because you're not going to be given those rules. You've got to remember those rules. The electronegativity, the fact that hydrogen has only got 1 electron to give away, so it's always going to be a +1. It can't be a +2. It doesn't have 2 electrons to do so. So to go and look at those, because when it comes to some of the more complex situations, you're going to need to apply those rules quite rigidly. Okay? So when they say to you, work out the oxidation number of manganese in all those 4 or 5 different, or sometimes even 6 of them, or sulfur, or those, please make sure that you do those. It's really, really worth getting those processes of assigning oxidation numbers well into your system for this part of the work. So let's have a look. And we can say, well, zinc on this side must be a 0 as well. I'm just going to move that actually down, put it underneath there. Zinc over here. The chlorine over here was a -1 times 2 is a -2. So zinc must be a +2. Over there, I'm just going to put that +2 there. And we can already see zinc has gone from +2 to 0. Manganese, I almost said. Magnesium, let's have a look here. That's a -1, that's a -2, that's a +2. So magnesium has gone from 0 to +2. So you can see here that to go from a +2 down to a 0, let's correlate it with what we had up here. The zinc went from a +2 to a 0. It must have gained electrons, right? It must have gained electrons, which is what it did. All right. So we had a gain in electrons. Okay, +2 to there, and that was gained electrons because it went from a positive to a negative. And on the other side, we had here lost electrons, right? And you can see in this situation the two half reactions that come out. The one is going to be the zinc went from a +2. Let me change it rather back to to black. Just that I think it makes it better to see it where you are. Okay. Let's see here, what have we got? We had here the zinc was a +2, and the zinc became a 2 electrons there, became uncharged, and over this side, the magnesium was a 0, it became Mg +2, and 2 electrons were given off, and there's our half reaction. And we had gain here, so oil rig gain is reduction, and this is oxidation. Right? Okay. So now let's move on to the next one. As I say, they do get more complex than that, obviously. But let's have a look at the next question that is on that download sheet that you've got, hopefully, in front of you. Okay. Then the next one. All right. Oh, sorry. What I forgot to mention, of course, in the previous one is the fact. Let me go back to it. Let's just go back here. Can you see that in this situation here, let's go to the top one first. Let's just do it in blue. Can you see here the chlorine stayed dissolved and stayed dissolved on the other side? In other words, the chlorine spectator ion. Okay, it played no role in this process. Okay, let's have a look at the next one, shall we? Okay, just change my pen back to black, and they say that in this one here, okay, consider the following reactions, and they've given some numbers to us. They say identify the redox reactions. Let's have a look at the first one, shall we? Right. They say number 1, A was 2Na solid plus 2H2O liquid goes to NaOH. Okay, just get rid of you. NaOH aqueous plus H2 gas. A reaction we know, isn't it? A metal, sodium on water, and it gives us sodium hydroxide, and it gives us the hydrogen gas gets bubbled off. Well, let's have a look what has happened. Let's assign oxidation numbers to this, because we need to see if it's a redox reaction or not, right? Let's assign some oxidation numbers. I'm just going to stick with green for the moment. Oxidation number, this is an element, so it's a 0. This on this side, I always go through and do my elements first. Now let's have a look. Oxygen here is -2. Over there, hydrogen is +1 times 2 of them, +2. Let's have a look here. Hydrogen is there, is that? Well, let's have a look here. H is +1 -2, and on this side, we've got a +1. So let's see what's happened here. The sodium has gone from 0 to A. In other words, it's melted, hasn't it? Okay. Then we can say here, the oxygen, okay, has in fact, I'm going to put that in blue. The oxygen has in fact stayed at a -2. All right. But what happened to the hydrogen? All right. The hydrogen, in essence, do this in red. The hydrogen over here went from to 0. All right? So there we've got a gain and a loss. Okay, gain of electrons here and a loss of electrons above it. Now let's put these two together, shall we? Because it's quite critical the way we look at it. Let's have a look. Now I know if you've got the the half reaction schedule with you, of course you can use that as well. But let's see how that's built up. Well, first of all, the sodium, the Na, went from to Na plus 1. Therefore, what happened? It must have lost an electron over there. So that's lost of an electron. Oxidation is loss, oil, oxidation. And what happened over here? The hydrogen was a plus 1, and it went to H2, didn't it? Right? H2 was the gas. Now, we always write, be careful of iodine, bromine, chlorine, fluorine, and the hydrogen, okay, and oxygen. Be careful of these because they must be diatomic. You can't have the H plus, let's say plus 1 electron going to an H. Okay? Okay? You can't have that. Why? Because we don't get H on its own. It is always A2, isn't it? It's H2 as a gas. Therefore, we need 2 of those and 2 of those. Because what is happening is we've got a hydrogen ion here and another one coming together. So in each, they both take an electron and then they form an H2, right? They're independent, H plus ions. They come along. This one gets an electron, that one gets an electron. They form together to form H2. So you can see here, okay, gain. So we've got reduction, right? Now we have to multiply through by 2 because we have to balance the electrons. There they are. So this one is going to be 2Na plus 2 electrons. Then we would add them together. At the end of the day, we would add them together and we would get the balanced reaction of 2Na plus 2H plus. Okay. I haven't balanced out with the, I'll do that now. Okay. Okay, I haven't balanced it out with the waters yet and things like that. So let's just, I'll tell you what, so as not to confuse you, until I get to that point where we do the balancing with using waters and the hydrogen ions and so on, let's just leave that as it is for the moment, shall we? But we've balanced the electrons. There's the 2 half reactions that we've been asked. So yes, it is an oxidation reduction reaction because there was an electron transfer. Let's have a look at the next one. H2S plus copper sulfate. All right. H2S, gas plus CuSO4. SO4 in aqueous, okay, leads to CuS solid. Obviously, it's a giveaway plus H2SO4. Aqueous. All right, what has happened here? Hydrogen sulfide gas, we've added to a solution of copper sulfate, and we've got a precipitate out. This is a precipitate over here. It's a solid, it drops out. We get copper sulfide coming out, and we get an acidic environment, sulfuric acid created. So, first of all, let's just check the balancing numbers. In this case, as I've written it down, it's balanced out. SO4, copper, yep. Okay, so that's cool. Now let's have a look and see what has happened here, shall we? Okay. Let's assign some oxidation numbers to it. Well, over here, let's start over here with the gas. H2S, it's a combined. So this is a plus 1. I always do them in 2 levels. Plus 1, that's going to be a plus 2, which means my sulfurs are minus 2 over there, right? Let's have a look here. Copper is a, from the copper sulfate, you know SO4 is a minus 2, so that's going to be a plus 2. That's a minus 2, minus 8. So what is sulfur in this case? Sulfur in this case is going to be plus 6, isn't it? Right? Over here, I hope you get that, because I've added plus 2, let me just show you here, plus 2 plus x, which is sulfur, minus 8 must be 0, because the sum must be equal to the overall charge, and the overall charge of this, it's not an ion, therefore it must be 0, so therefore x is going to be equal to plus 6, which is the charge on sulfur. Okay. Now, let's have a look here. Sulfide is a minus 2 and a plus 2. HSO4 minus 2 minus 8 plus 2. It's plus 1 times 2 there. And it's going to be a plus 6. So let's have a look. Well, that stayed the same. The H has stayed the same. The copper has stayed the same. And the oxygen has stayed the same. In fact, I don't want to do that. I want to do this. Can you see? The SO4 has gone there. The H2 has linked with that. And the S and the copper have just got together to form copper sulfide. So what has happened here is that it's not a redox reaction. There's been no change in the oxidation state, right? And if there's no electron transfer, it's not a redox reaction. Okay? Let's look at the next one. The next one is 2NaOH plus SO2. 2NaOH plus SO2, a gas, going to Na2SO3. SO3, aqueous. Okay, NaOH is aqueous. Sorry, I should have put that in earlier. Plus H2O. Okay, now let's have a look at what has happened to this one, shall we? Once again, let's have a look here. Na is a plus 1, we know. Hydrogen, plus 1. Oxygen, minus 2. Whoops, I should have done those in green. I've been doing them in green all the way up to now. Okay, so we've got that. O2, minus 2, minus 4, plus 4. Right? Now let's have a look and see. O3 over there, so we've got minus 2 over there. Each one times 3 is a minus 6. Sodium, group 1, which means it's a plus 1, plus 2. So therefore, sulfur, in this case, remember, plus 2, plus X, let's say. X minus 6 must be 0. So therefore, X is going to be equal to 6 minus 2, which is equal to 4. So sulfur is at plus 4. Okay. Now, hydrogen, plus 1, plus 2, and minus 2. Once again, if we have a look at this, you can see there's been no change. Sodium, let's just change this to blue. Sodium is still plus 1. Oxygen, minus 2, minus 2, minus 2. Hydrogen, plus 1. And sulfur, the other most important one in this, has stayed at plus 4. Now, you know sulfur can go from plus 4, minus 2, and it can take a few various forms, right? So this is not a redox reaction once again. Okay? Let's have a look at the next one. H2 plus I2. Okay. H2 plus I2, both gases in this case, all right, are going to go to 2HI. Gas, gas, and we can assign oxidation numbers. They're elements, which means they have got an oxidation number of 0, all right? And over here, hydrogen is a plus 1 and iodine a minus 1. That's its valency. Can you see there we had a change, and here the hydrogen has changed from 0 to plus 1, from 0 to minus 1, which means over here, that one over there has gained an electron, hasn't it? because it was now it's gone to a -1. So it's pinched an electron from hydrogen. If you remember, that's what it does, doesn't it? Iodine has got a stronger electronegativity, so it pinched the electron. All right. So, and then this one lost. So yes, it's a redox reaction. And what would our half reactions be? Let me go back to do it in black. Okay, our half reaction would be H2 has changed to H plus, right? But there's two of them again, so there must be that, and 2 electrons were lost off the side, and the I2 over here went to I minus, okay, and what did it do? But hang on, there's 2 of those, so I must have had 2, remember? These 2 split up into 2 individual negative ions, don't they? And what happens is 2 electrons are over there. In this case, you can just add them and you'll get the final reaction coming out. Okay. What I'm going to do is I'm going to move on with the next section, which is some more complicated ones where we're going to use acidic and an alkaline environment. We're going to do some of the ones where they're not as straightforward as these are. Okay. And as I say, I reiterate again, it really is important to get a good handle on this, because it's a key area for most of the reactions in the future. Thanks, and hope to see you back on the next one, and we're going to do some more complicated ones. Thanks.